Hi everybody, Mr. Johnson again, coming to you from my basement in Seattle. It is September 20th, 2020. Some good news in our lives right now is that the smoke that's been pervading the Puget Sound for, a week and a half seems to have pushed its way out. Sad news is Ruth Bader Ginsburg passed away on Saturday, leaving a void in my life, and I would imagine in many of your lives as well. So we're going to be doing section 3.2 today. It's page 117 in your ebook, page 109 in your textbook, and we're going to be talking about the mole. We're going to break this lecture series up into three parts. While it's all to me one lecture, it's all tied together. I'm going to break it up into three separate parts, post those three separate parts to you so you can break it up as well to make it a little bit easier to learn. I'm excited to be with you today and to be talking with you about the topic on hand, because we're going to be talking about the mole today and using dimensional analysis, and there's no more fundamental concept arguably in chemistry than the mole concept, and I'd argue there's no more important skill, useful skill in chemistry than dimensional analysis. So we get to see those two things come together today. Consider yourselves fortunate. So the mole we're talking about today is not the little ground-dwelling, semi-blind mammalian creature that wreaks havoc on lawns, nor is it the highly pigmented, sometimes hairy outgrowth that some of us experience, but rather a number we use in chemistry that takes us from the atomic, the subatomic world, the world of atoms, molecules, electrons, protons, to the macroscopic world, the world we live in, the world we can see. So like I mentioned a moment ago, a mole is this very large number. It's a fixed number. It's referred to as Avogadro's number. This large number is referred to as Avogadro's number. And you can see in our book here, it is 6.02214179 times 10 to the 23. We are going to use and publish, though, just 6.022 times 10 to the 23 whenever we use a mole in calculations, and that's common. Our book says that just like a dozen is 12 of anything, if you have a dozen pigs, I'm not sure why I said pigs, but I did. You've got 12 pigs, a dozen donuts, 12 donuts. So too is that true of the mole. If you have a mole of anything, that is approximately 6.02 times 10 to 23 of that thing. It's an enormous number, because as enormous as that number is, atoms are small. Again, it takes us from the world of atoms, individual atoms, to the macroscopic world. In fact, if you had a mole of moles that covered the entire surface of the Earth, that mole of moles would be 2,000 feet thick. Moles are fairly small. The Earth is fairly big. A mole of moles, that many moles, would cover the Earth about 2,000 feet thick. So that's just to give you some perspective on how big that number is. If we look toward the top of this page, which I skipped earlier, there's another definition for a mole here, which we'll come back to in a bit when we talk about molar mass, and that says that a mole is a quantity equal to the number of atoms in the atomic mass of any element expressed in grams, which again is 6.02 times 10 to the 23, but we'll come back to the meaningful of that later. All right, so what we're going to do next is use Avogadro's number, or a mole of items, to convert between how many moles of that substance we have to how many actual items there is. Kind of like we could convert between 3 dozen eggs to an individual number of eggs by multiplying by 12 eggs per dozen to get 36. So can we go from moles of atoms or molecules to the individual numbers of atoms or molecules, or we can go backward from an individual number of atoms or molecules to moles. And this graphic is showing us how we can do that. So does this table give us the information we need to be able to do that. If we look at the equivalent statement between a mole and the number of items in a mole, we're reminded that, again, it's 1 mole equals 6.02 times 10 to the 23 items. Any equivalence can be written as a conversion factor, a fraction where the numerator and denominator equal each other. They only equal each other, though, remember, if they have units associated with them. 1 does not equal 6.02 times 10 to the 23, but 1 mole equals 6.02 times 10 to the 23 items. I want to remind you as well that any conversion factor can be written as its reciprocal. So instead of having 602 times 10 to the 23 on top and 1 mole on the bottom, we can have 1 mole on top and 602 10 to the 23 on the bottom. And which one we use is based on whether we're going from moles to an individual number of items or from an individual number of items to moles. And I'm going to go through a sample problem with you right now to show you how to use these conversion factors. So I'm going to flip my page to page 119 of the ebook or 111 of the textbook and solve a problem with you. All right, so we're now looking at practice problem 2 at the top of that page I just flipped to. And we're looking at 30.0 moles of water equaling blank number of molecules. So we're going to figure out how many molecules of water there are in 30 moles. While many of you may know how to do this intuitively, could do it without dimensional analysis, I'm going to ask, in fact require, that we solve all of our problems in here using dimensional analysis if that's possible. And that is the case for this one. So I'm going to go to my whiteboard now and solve this problem with you on my whiteboard. If you want to give this a shot on your own first before you see me solve it, take a moment to solve this problem using dimensional analysis, and then take a peek at my solution and see how you did. All right, so I've written 30.0 moles of water. I always want to start by writing my given quantity and its unit and the formula of the substance that we're dealing with in the problem, which will become particularly important in stoichiometry when we convert between one type of substance and another. But I want us to be getting into the habit right now. I'm going to put this into a dimensional analysis box. And unless my unit is fractional, where there's a numerator and a denominator, I always put my given value and its unit in the numerator of the dimensional analysis box. And then either we put nothing on the bottom, or I like to put a 1 there, just so I know not to put anything else. You can either put nothing on the denominator or a 1. All right, so here's where I'm going to write my conversion factor that takes me between moles and, in this case, molecules of water, because water is a substance, a molecular substance. It's molecules of water. If it were an element, then it would be atoms, but in this case it's molecules. I don't memorize what should go where. I always use the basic principle of dimensional analysis, which is about unit cancellation, knowing that whatever unit is here will need to go here in order for it to cancel. So because I've got moles on top, I put 1 mole on the bottom. And no, I don't need to write water, but I'm going to, so 1 mole of water on the bottom. And then what it's equal to in molecules is 6.022 times 10 to the 23 molecules of water. Moles cancels, that's why I put moles in the denominator of my conversion factor here. I'm left with molecules as my unit, and when I multiply 30.0 times 6.022 times 10 to the 23, I get 1.8066 times 10 to the 23. Remember that when you're entering numbers in scientific notation into your calculator, to not hit the times button there, but rather the EE or EXP button. So I did 6.022 EXP or EE23 when I put it into my calculator. We've got to round all of our answers to the right number of significant figures. Since this is multiplication division, which is what dimensional analysis will always be, I round to sig figs. And because 30.0 has the fewest, I need to round this to 1.81 times 10 to the 23 molecules of water. And there's my final answer. All right, so I've just scrolled down. I'm now on practice problem 2 on that same page, and I'm going to solve this with you as well on my whiteboard. If you feel like you've got the hang of this and that you could go on your own from molecules to moles, which is the other way we just went, feel free to skip ahead, but I'm going to solve this for you right now. So I've written my starting value, 2.25 times 10 to the 24, along with its unit and the formula of the substance in the, once again, upper left-hand corner of my dimensional analysis box. Put either nothing in the denominator or a 1, and I want to recognize that I'm starting with molecules now, and my goal is to get to moles. So this time I've got to put 1 mole on top and Avogadro's number, or 6.022 times 10 to the 23 molecules on the bottom. So 6.022 times 10 to the 23 molecules of CO2, 1 mole, CO2 on the top. Molecules of CO2 cancels. I'm left with moles, and I get 3.7363. Need to round to the right number of significant figures because, once again, this is all multiplication division. 2.25 is my fewest sig figs. That's greater than 6.022. Remember, I only use the coefficient when determining sig figs in scientific notation. So I round this to 3 significant figures. 1, 2, 3. My 3 will round up because 6 is 5 or higher, and so I get 3.74 moles of CO2 as my final answer.